Now we need to look at how we're actually going to use Newton's laws. So when you're approaching a problem, the first step is to identify any forces that are acting on the objects. So you draw a free body diagram for everything. Make sure you label where the forces are applied, which forces they are, change the length of the arrows to indicate which one's stronger or weaker, and indicate what is causing the force, whether it's the earth pulling on the object or the table or the string, whatever it is, exerting the force on the object. And then you indicate the acceleration. Don't include other forces on the system or other forces that the system exerts on something else. What's causing the force. And then you basically turn that equation, the diagram, into the equation. So you add up all the forces on the objects, and we'll talk about later, you can also separate out the horizontal and vertical components. And the net force, once you've added up all those forces on your free body diagram, that will equal mass times acceleration. So it isn't force equals ma, it's the net force. The vector sum of all the forces equals mass times acceleration. So we're going to do an example with the idea of what's called Atwood's machine to determine what the acceleration of this object is. So here, just to indicate a free body diagram, how I'm going to type that up. So the acceleration, we know mass 1 is bigger, mass 2 is smaller, so mass 1 is going to accelerate downwards, mass 2 is going to accelerate upwards. Mass 1, its free body diagram, is an upward tension force that's less than its weight. And there's the downward force of the Earth that is pulling it toward the center of the Earth. The very similar free body diagram for mass 2, except the tension force is greater than the weight in that case because it's accelerating upwards. So we plug that into Newton's second law, net force equals mass times acceleration. I can do that, I can take each of those equations that we found from the free body diagram and turn those into two equations, one for mass 1, one for mass 2. So mass 1, there's an upward force of tension and its weight is downward, equals mass times acceleration. Mass 2, upward force of tension, downward force of the Earth, that equals mass times acceleration. But the problem is, because they're coupled together, they have the exact same tension. So it's the same rope. You don't change the tension. We're going to pretend the rope is massless and ideal. It doesn't stretch. It doesn't kind of twist or anything like that. Because they're connected, the accelerations are the same, just in the opposite directions. That gives us actually an easier way to solve this problem. This problem, this full version of Newton's second law, allows us to solve for any internal forces in our system, the tension force in this case. But for coupled motion, when things are moving together, the tension force is that internal force. It's part of our system. The rope is accelerating along with the masses. The weight is the external force, but the weight on each side is trying to get it to rotate a different direction. So the net force is the sum of the external forces. So what I'm going to do is say, all right, I'm going to say I know that mass 1 is going to accelerate downwards, so I'm just going to use that as my positive direction. So mass 1 pulling downwards, mass 2, its weight actually tries to slow down mass 1 because it's in the opposite direction. So the net force is the difference in those two forces because the rope makes them fight each other. So they move together, but their masses are the sum of both of them. Because mass 1 and mass 2 are both moving together, we use their total mass together. So that basically becomes net force equals mass times acceleration. So the net force is mass 1 is mass 1 is fighting against mass 2 in their weight. So the acceleration due to gravity, we use that. So they're fighting there, but they're together, so we add their masses. So it turns out the acceleration is going to be slightly less than the acceleration due to gravity because they're fighting each other.